Hello, welcome to Advanced Composites. Today is the 5th day of the ongoing course of this course, which is into its 3rd week, and what we will do is we will today have a very similar discussion on lines which we had yesterday. Yesterday we had developed an expression between force resultants and mid-plane strains and curvatures. Today we will develop a similar relation between moment resultants and mid-plane strains and mid-plane curvatures. So, we will again use the similar mathematical process, but we may not necessarily go into that greater detail because the basics have already been developed earlier, but we know that moment resultant is what? It is equal to integral of sigma times z times dz, right. This is the basic expression. Now, essentially these are 3 equations. There is an equation for sigma x, there is an equation for sigma y, and there is an equation for tau xy, and this integral happens between the limits minus h over 2 to h over 2, where h is the thickness of the plate. But we know that sigma vector is what? Is nothing but q bar vector, and it changes from one layer to a layer because the material is changing. So, we have to talk about kth layer. So, for kth layer sigma is like this. Okay. So, we plug this back into this and eventually we get moment resultant equals q bar times epsilon naught dz plus minus h over 2 q bar. So, actually this k subscript should be outside, and there is a z here times the curvature vector dz, and because this q matrix is discontinuous across different layers. So, I will integrate within a layer, and then as I move from one layer to other layer I will sum up things. So, I can write it as m vector is equal to, so there should be z here and there is a z square there. So, it is a summation k is equal to 1 to n, q bar is constant over a thickness and strain is constant over the entire thickness times integral of z dz h k minus 1 to h k plus summation k is equal to 1 to n q bar for the kth layer times curvature vector times integral h k minus 1 to h k z square dz. So, if I do this and I add up all the terms, then this entire thing we have already defined as a B matrix, which is 3 by 3. But now we have a new term involving z square dz integral, and which is this, and this gives us a D matrix, and this is also a 3 by 3 matrix. Okay. So, we say that the moment resultant vector is equal to the B matrix times the mid plane strain plus a D matrix, which is again 3 by 3 times the mid plane curvature. And we have already defined the B matrix, so we will not do that again, but we will define that Dij is equal to summation of Qij for kth layer times Hk cube minus Hk minus 1 cube into 1 by 3. Overall, we can say, so we can assemble all these relations for moment and force resultants, and we can say that force resultants and moment resultants, they are what? They can be calculated from this large set of relations. So, you have mid plane strain vector and mid plane curvature vector, and this is A matrix, B matrix, P matrix, and this is D matrix, and all these are also vectors of size 3. Okay. So, this is a 6 by, so these are 6 equations, and this is a 6 by 6 matrix. Okay. So, this is what I wanted to discuss. Now that we have developed relations for these, we will give these matrices A, B and D some names. So, the A matrix is called extensional stiffness matrix. Okay. The B matrix is called bending, no I am sorry, it is called coupling stiffness matrix, and the D matrix is called bending stiffness matrix. So, we will spend a moment trying to understand why these things have been given these names. So, consider a case that we have a situation where B is 0, where B is 0. If B is 0, then N can be calculated if we know A and epsilon only, we do not need to know K. Essentially what it tells us is that A matrix helps us define how much the material extends by, stretches or gets compressed, particularly it gets compressed and in presence of stresses, extensional stresses and extensional strains. And similarly the D matrix influences how much the system bends. If the D matrix values are extremely large, then the bending will be very small and vice versa. So, that is why it is bending stiffness matrix. And the B matrix is a strange creature, it is a coupling matrix, and what it tells us is that if B matrix is not 0, then if we try to stretch, if I apply just a plate, if I have a plate and I am just trying to stretch it, and if B matrix is not 0, then the material will not only get stretched, but it will also bend. And similarly, if I try to bend a plate and if the B matrix is not 0, it will not only bend, but it will also get stretched. So, that is why it is called a coupling matrix. So, this is the understanding behind their nomenclature. The next thing what we will do is we will discuss in next few minutes how do we provide names to different lamination sequences. So, nomenclature. For lamination sequences. So, suppose there is this is the mid plane, let us say there are several layers, and let us say what I will do is I will put their angles here 45, minus 45, 0, 90, 90, 90, 0, minus 45, 45, okay, and we will just. So, these are the orientations, and we assume that thickness and material is same for each layer. If that is the case, then we can designate the lamination sequence of this. So, we always start from top and we go down. So, we say 45 and then there is a minus 45 next to it. So, we say plus and minus 45. We will just rectify this. I think I had drawn it correct, but then so suppose this is the lamination sequence, then these two are plus 45 and minus 45. So, I write plus 45 and minus 45. Then there is a 0-degree layer. So, I separate it by a slash, and then there are 4 90-degree layers, but this is the mid plane. This is the mid plane, and mid plane is passing through this thing. So, I write 90, and then all other layers are just mirrored because this is the plane of symmetry. So, I just say symmetric. In a long way, this if the moment I write S, essentially what it means is that the lamination sequence is plus 45, minus 45, 0, 90, and there are 2 layers above the mid plane. So, this is 92. So, 90, 90, this is the mid plane, 90, 90, 0, minus 45 and 45. This is what it means. Okay. So, we will very quickly write down some rules. So, whenever we express it in such a format, we assume that we say that each layer orientation is assigned with respect to x axis. So, this x axis does not change, it is a universal axis. Then we use these as separators between layers. We always go from top to bottom. What else? If there are 2 layers next to each other and they have the same orientation, so adjacent layers with same theta, then we give a subscript. If the laminate is symmetric about mid plane, then we use a subscript S, and we can also use plus theta, minus theta. This can also be written as plus minus theta. Similarly, if the lamination sequence has a negative theta and plus theta, then this can also be written as minus plus theta. Okay. So, these are some broad principles through which we determine lamination, we prescribe lamination sequence. The next thing we will start discussing is role of A16, A26, B matrix entire and D16 and D26, these elements. Okay. Now, a detailed discussion on these elements we have already had in our earlier lectures in the introductory course, but for purposes of completeness and just a quick review, we will discuss these things and explain their influence. So, what does A16 and A26 do? A16 and A26, these two elements couple extensional strains with shear stresses, and they also couple shear strains with extensional stresses. So, what does this mean? It means that if B matrix is 0, in such a situation, suppose you have a system when A16 and A26 are not 0, and then in that case if you subject the plate to a pure tension stress, it will exhibit not only extensional stresses, but it will also shear. And if you expose it to pure shear stress, it will not only get a shear strain, but it will also experience or exhibit extensional strains. So, this is about A16 and A26. Okay. Then the B matrix, it couples extensional strain with moment resultants, okay, and it also couples bending response with force resultants. Okay. So, what does this mean in plain words? That if the B matrix is not 0 and I suppose pull the plate, then the plate will not only get stretched, but it will also bend. And if the B matrix is not 0 and if I try to bend the plate, and if B matrix is not 0, then it will not only bend, but it will also get stretched or compressed. So, that is why it is a coupling matrix. And then when finally we look at D16 and D26. So, both these terms, they couple bending curvature with MXY. So, MXY is a twisting thing. Okay. So, it bending curvature, and they also couple twist curvature with MX and MY. So, what does this mean? So, just to show this, suppose I have a plate and I try to bend it, and if D16 and D26 is not 0, it will not only bend, but it will also do this type of thing, twisting. And if I try to twist it, it will not only get twisted, but it will also do this thing, bending. So, it couples bending and twisting responses of the system. So, D16 and D26 are of this nature. So, this is the overview of this all ABD matrices and something special about some of these particular members A16, A26, the B matrix and D16 and D26. And tomorrow we will have some further discussion on these terms, and we will learn how to make these elements 0 or minimize these values. So, that concludes our discussion for today, and I look forward to seeing you tomorrow. Thank you.